Now we're going to learn about limited direct execution. This is a solution to the problem of how do you run multiple processes on the same physical processor. If you remember, every process that's running has its own set of registers and state that has to be saved somehow when we move from process to process, and somehow we want to give the user the illusion that all of these processes are running at the same time, even though there's only one physical processor. So the broad idea is called time sharing. So what we're going to do is we're going to run process 1 for a little bit of time, then process 2 for a little bit of time, then process 3 for a little bit of time, and so on. The way we accomplish this is through what we call limited direct execution. So let me sort of walk you through some of the different parts of it. So if we look at the iPad, now we have process 1, and then we have process 2, and then they have to run on the same processor. Of course, each process has its own set of registers and state and so on, right? Now, one of our goals in doing limited direct execution is that we want to be safe and we want to be fast. So what do we mean by safe? So let's say we allow P1 to run, right? Or let me actually cover fast first and then we'll get to safe. So we want our execution to be fast. So if you're running two processes at the same time, your machine should not run half-fast slow, right? If we had a computer like that, nobody would buy it. So we want our computer to run as fast as possible. And the way we're going to do that is by basically saying we're going to run each process directly on the hardware. Right, so when P1 is running, there's nothing separating it from the hardware. The process is running directly on the hardware and using registers and the stack and so on and so forth. So it's direct. That's where this part of the name comes from. We are directly running it on the processor. However, if we just did this is not very safe. Right, and the reason is, let's say P1 is a malicious program, right? It's or let's say it's a buggy program. So it has an infinite loop in the program, and we allow it to run on the processor, and it just runs forever, never letting the OS or the processor, the next process P2 run. So if we just did direct execution, it's not very safe, and that's where the limited part of it comes in. Right. So if we remember from our previous unit, we have this concept of a timer interrupt. So every so often, the hardware is going to have a timer interrupt, which basically says, some amount of time has done, and then the whatever process is currently executing has to be stopped. Right. So that's where the timer interrupt comes in, and there's a bunch of stuff going on when we get a timer interrupt. So for that, let me sort of talk a little bit about what a trap is. So let's see. So let's talk about traps and and interrupts. So when basically the process P1 is certain lines of code and it's continuing to execute, right? And at this point of time, let's say at this point here, we get a timer interrupt. So what really happens is that the hardware, your processor basically, is saying to P1, this has to stop. Now, at this point of time, there's a bunch of stuff that needs to happen. So in your processor, there is something called a trap table. And similarly, there is also an interrupt handler table. So this is one thing, and then interrupt handler. So what this says is, let's say you get a timer interrupt, right? And by the way, timer interrupt is not the only kind of interrupt that you can get. Let's say you wanted to write something to storage, and then after some amount of time, the storage device says like, I'm done writing. So you get an interrupt for that. So there can be all kinds of different interrupts that you can get from hardware to say that some event has occurred, right? So in the case of a timer interrupt, what's really happening is that the timer interrupt is saying, hey, you set this timer for like 5 milliseconds or whatever, and at this point of time, it's done. So the hardware basically has to know what to do when it gets this timer interrupt, and that's what the interrupt handler accomplishes. So it basically says, when you get this timer interrupt, go and execute this piece of code. That's basically what it says. And the way the operating system takes control is by putting stuff carefully into this interrupt handler. So for example, this interrupt handler could basically say, every time you get a timer interrupt, run the OS. Right? So now it doesn't matter like how buggy your process is, right? P1 could be an infinite loop. It's a timer interrupt, boom, the hardware is going to run the OS instead. So because of this, now we have handled the safety part of like limited direct execution, right? So we don't really mind if like there's a buggy process or a malicious process. Every time there's a timer interrupt, the OS is going to run. So that's one sort of like part of it. But again, if we think about it, there are like details here, right? So for example, let's say we allow the process P1 to run, and it's very sneaky process. It goes in and it changes the timer interrupt handler. So it says, instead of like running the OS, whenever you get a timer interrupt, just run P1 instead. And then P1 would say like, oh, like forget about the interrupt, like let's continue running. So if this was actually possible, P1 could run for an infinite amount of time, even though we have timer interrupts. So this actually brings us to the concept of privileged state. So on your processor, there's certain state that not everybody can change. Right? That's the definition of a privileged state. And for example, the interrupt handler is one such thing. So to sort of like differentiate who can read and write a privileged state, there are two modes. One is called the user mode. So normally when your applications run, they run in user mode. And there's also kernel mode. So the kernel is just another name for the operating system. So what this basically means is, in kernel mode, you are now going to be you have the privilege to actually read and write interrupt handlers, tap handlers, and privileged state like that, right? So this is the other part that's really needed to make this whole sort of like business run. So here's how it would happen, right? So there is a let's say there is a bit in the processor which says like, what state we are currently running in. So if it's 0, you are in user mode. If it's 1, you're in kernel mode. Now, if you are trying to write to the interrupt handler, that can only happen when this particular bit is set to 1. So that's really how it ensures that nobody else can touch the interrupt handler. Only when this state is 1 can you actually change the interrupt handler. When your processor is starting up, the OS does some amount of like starting bookkeeping, right? So initially it'll set up all the interrupt handlers. When the process starts up, it's going to be in privileged mode. So it's going to set up the interrupt handler. It's going to be in like mode 1, and then once it's all done, then it's going to switch to mode 0 and then say, I'm done with all the sort of like initial bookkeeping I need to do. Now the user process can run. Right, so this is sort of like one of the important bits as to how we can allow buggy or malicious processes to run and still not, like have it end up corrupting the operating system or doing other stuff we don't want it to do. So one more sort of like detail here is, if your application is running in user mode, how does it actually go to kernel mode and back? And this thing is called the system call. Right? So this interface between user mode and kernel mode is what is called a system call. Okay, so let's look a little, go into that in a little bit more detail. So your application is sort of like running along. This is in user mode. Right? So in user mode, your application can do anything that doesn't actually touch privileged state. So let's say it wants to, like add numbers, display something on screen, all of that is perfectly fine, right? Like, well, not display something on screen, but let's say it wants to add numbers. Like that's totally fine, and it can continue to do that without ever talking to the operating system. Let's say there is some point at which it does need to talk to the operating system. For example, let's say it wants to write to a file. Now, writing to a file involves the actual device that is attached to your operating system. And if we let any process write directly to the device, it's going to be, it's not going to be safe. Because of this, access to devices is carefully controlled by the operating system, and there are many system calls that allow the applications to access devices, set interrupt handlers, and so on and so forth. So let's say the application is going to, let's say the application wants to actually write to a device. It calls the write system call. Now what this write system call does is it's going to invoke a trap. Now remember in our interrupt handler we saw this previously where you would get a timer interrupt, and then the timer interrupt, that will be a table, and then the hardware looks in this table and then it says, oh, you have a timer interrupt, you have to run this code. A trap handler works in a very similar way, right? So you have a table which says you have these different kinds of traps. And then when you get this particular kind of trap, this is the code that you should run. Okay, now one of these traps is going to be for a system call. So every time you want to do a system call, you invoke a particular kind of trap. And here's the different things that happens there. So when you have a trap, you're currently in user mode, right? So one thing that needs to happen is that you are currently executing something in user space. You have to save that state, right? And you do that by something called a context switch, which we'll talk about next. But just think about it as like you're saving state. Okay, so whatever you are currently working on in user mode, you save that state, and then when you invoke this trap, you need to tell the trap basically what to do. Like every system call does something different when it goes into the operating system. So you need to tell the operating system what it is that you want it to do. And so you basically what you do is you write the arguments for a system call in different locations. So for example, like arg1, arg2, and so on. So let's say you're writing something to a file. This could be file name or file descriptor. This could be the content, how many bytes there are, and so on. So you put all these arguments in sort of like predefined locations, and then you invoke a trap. And on x86, this is going to be like 80, your system call that you're invoking. And when this trap happens, then what really happens is that the hardware says, we have a trap, let's go look in the trap handler table. The trap handler table will say, oh, you got like a system called trap, this is what you should do. And at this point of time, so this will, when you have a trap, this goes to the trap handler table. And then the code there will invoke the operating system. So to go through this again, you're running in user mode, you call a system call. The system call makes sure that you save the state of whatever it is that you're working on in user mode. Then it will invoke a trap. This trap will go look in a trap handler table. This trap handler will say, oh, the user is trying to do a write system call. Go invoke the OS so that it can handle that. So that's really the path from user mode to OS mode. And of course, while doing the trap instruction, you change privilege level. So you started off in user mode and then you saved your state and so on. When you invoke your trap, you go from user mode to kernel mode, right? Now, one thing that you should sort of like note about this is that user mode can't really say, go to kernel mode and do this particular thing. So it's not saying like, go to address 1000 and then like execute whatever is in address 1000. If we allow user mode to say stuff like that, this would lead to like a lot of security risks, because user mode can put like really bad stuff in address 1000, and so when the OS tries to execute whatever is in address 1000, it could crash. So the user mode cannot tell the OS, here's a specific address I want you to go to, or like here is the code that I want to execute. All it can really do is it can make a request. You can say, I want to do a system call, and this system call is going to invoke, like all these different arguments, and please look at these arguments, and if everything is correct, do this work for me. And all the user mode can do is it can just invoke the trap, right? And the trap, you can think of it as, say, it's a request to the operating system, right? Oh, great operating system who has privilege and I don't, please do this for me. But you can't really say exactly what you want the operating system to do. The operating system will take a look at your arguments, and if the arguments are not well formed, or you're trying to do something weird, it will reject your system call, right? So for example, you're trying to write to a file that doesn't exist, right? It would, instead of like doing weird stuff, the operating system would look at your arguments and would say, oh, this file doesn't even exist, and it would just return from the trap, right? So this is really the mechanism by which user mode can ask the kernel mode to do something for it, right? And one sort of like detail that's required to make all of this happen is the context switch. So now you see that the context switch is really an important part of like how a trap and how a system call works. So next we're going to learn how a context switch works, and how we can run process 1 for some time and then switch to process 2 and still have everything work in our system.